Hassler here. So I'm going to do some notes on section 4.4. This is introducing related rates. Related rates are applications of implicit differentiation. So it only seems appropriate that we skip ahead to this section. We'll come back and finish section 3 later. So the goal is to write an equation that creates a relationship using different variables, then differentiate with respect to time. And so these problems are a little bit different because time is always going to be our independent variable. So that means that time is always the independent variable. All right, so time is always the independent variable. Even though you might not always see the word time mentioned, it's this like unspoken word that time is the independent variable. So the first scenario is that a rectangle is undergoing changes to its length and width over time. Find an equation that relates how the perimeter of the rectangle is changing over time. And when I see this terminology, changing over time, I'm thinking about something like a rate of change. And when I think about a rate of change, I'm thinking about a derivative. So the first thing that I would do is I would draw a rectangle. And after I draw this rectangle, I might write down, that this would be my width. So the opposite side is width, and this is my length. I'll use a cursive L. So the opposite side is my length, and we're talking about perimeter. And so AP expects you to know that perimeter is equal to, the sum of all the sides. So I have 2 L's and I have 2 W's. But it says find an equation that relates how the perimeter is changing over time. What that really means is then I would take the derivative with respect to t. In these related rates, we're looking at how, in this case, the perimeter changes over a period of time, so how the side lengths are changing over that period of time. Over that period of time, time is that independent variable. And so notice that the p, the function for the perimeter, is different than the independent variable. And so the derivative of p is, p prime, or dp dt. And I am going to strongly encourage you to use this Leibniz notation. Since t is this unspoken independent variable, t does not show up in my red equation anywhere. And so I want to make it known that t is the independent variable. I do that by saying the notation dp dt equals, now I'm going to take the derivative of 2L, but again, L is not the same variable as the independent variable. And so the derivative of 2L is 2 times the derivative of L with respect to t. So it's this implicit differentiation that's happening, plus the derivative of 2W with respect to t. Those are not the same variable. So the derivative of 2W is 2 times the derivative of W with respect to t. And that's it. That's all I'm doing today, is just coming up with these derivative equations. B says find an equation that relates how the area of the rectangle is changing over time. So if you recall, the area of a rectangle is length times width, or you could say base times height. So again, area is length times width. Oh no. Times means I have to use a product rule when I go to take this derivative, because again, it says changing over time, which makes me think of a rate of change or a derivative. Changing over time means I'm going to take the derivative with respect to time. T is my independent variable. And so the derivative of A, A is a different variable than my independent variable. So the derivative of A is just dA dt, or A prime, but I strongly encourage dA dt since t does not show up in my purple equation. And then this is where I have to do the product rule. So the derivative of L would be dL dt times the second function W plus The derivative of w is dw dt times the first function L. And that's it. That's all I can do. Okay. All right, let's talk about the next example. The next example is a circle. They like to work with circles quite a bit. So a circle is undergoing change to its radius over time. Find an equation that relates how the area of the circle is changing over time. So again, I have a circle, and here's the radius. When I see is changing over time, I'm thinking about what I talked about up there, right? Rate of change, or find a derivative. The area of a circle is pi r squared. AP expects you to know the formulas I've discussed so far. And I want to take the derivative with respect to time. I want to know how this is changing, the area is changing, the radius is changing over a period of time. So again, the derivative of A, well, that's different than the independent variable. So the derivative of A is dA dt. Now, pi is a constant. So it's kind of like me saying 3r squared, if that makes you feel more comfortable. Except I can't use 3, I have to use pi. So I'm going to apply my power rule, right? Take the exponent, multiply by the constant, subtract 1 from the exponent, I get 2 pi r. But r and t are not the same variable, so I have to multiply by dr dt. And I'm done. I took the derivative with respect to time. Find an equation that relates how the circumference of the circle is changing over time. Well, circumference is equal to 2 pi r. Or you could say circumference is equal to pi d, right? If I double the radius, I get the diameter. And so it doesn't matter which one you use. I'll do the derivative for both. Again, we're taking the derivative with respect to time. You might be thinking, well, how do I know which one to choose? And it would be based on the information that's given. So if a problem gives you information based on the radius, I would do c equals 2 pi r. If the information gives you the diameter, then I would maybe choose pi d. Doesn't matter. So again, derivative of circumference, dc dt. Those are different variables. Again, 2 pi, that's a constant, and the derivative of this linear function, 2 pi r is the variable, would be 2 pi. But because r and t are different, I have to multiply by the derivative of r with respect to t. So there's that version. Or if I use the c equals pi d, again, I'm going to take the derivative with respect to t. Pi is a constant. Okay, so the derivative of c is dc dt. Equal to the derivative of pi d is just pi, but dd dt feels weird, but that's what it is. Okay, and so you have those two options. Finally, we have this last one, and this one is actually a very common scenario, and the best way to do this is to draw a picture. So it says a police car approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. So those of us who are directionally challenged, north, east, south, west. So a police car approaching a right-angled intersection. There we go, right angle. From the north. So my police car is coming from the north. You can draw a car if you need to. Is chasing a speeding car that has turned the corner and is now moving straight east. So here's my speeding car, and it's moving east. Set up a relationship to show how the distances of the cars are changing. Again, we're looking at a rate here. We're looking at the rate of the distances between these two vehicles. The distance between these two vehicles, we'll go green. So if I have my police car here and my car that it's chasing here, the distance between them is this right here. The hypotenuse of that right triangle. Then find an equation that shows how these distances are changing related to each other with respect to time. So again, this feels very much like I'm finding a derivative. I'm going to be using this right angle. I'm going to call that hypotenuse d. That's the distance between the two cars. And, we got to write triangles, so this feels very much like the Pythagorean theorem. And Pythagorean theorem says a squared plus b squared equals c squared, but instead of c, I'm going to use d. So I'll call this a and I'll call this b. Nope, it does not matter which one you call which, okay? Sometimes you're told what to call things, but I can just call it those since I wasn't told. And so to find that distance, I would have to do a squared plus b squared equals d squared for my distances. And I want to find how those distances are changing, rate of change, with respect to time. So I'm going to take the derivative of each term with respect to time. None of these variables match the t. They're all different, which is why it's so important to include that t. So the derivative of a squared would be 2a, but because a and t are not the same variable, I got to keep that dA dt plus. The derivative of b squared is 2b times the derivative of b with respect to t equals, and then the derivative of d would be 2d times the derivative of d with respect to t. And that would be my equation. Okay, so 4.4 just practices setting up those equations and taking the derivative of those equations. In section 4.5, we will take it one step further and actually substitute values in that we know in order to solve these equations. Let me know if you have questions.